My name is A.L. Goldman. I teach physics at El Camino College. In some of our earlier videos, we were introduced to the idea of a conservative force. So in this video, we're going to be taking that idea of a conservative force and we're going to run with it and we're going to see what that leads us to. At this point in the course, we've been introduced to the idea of work. When an object moves through a displacement as a force acts on that object, we say that the force does work on the object. That work is equal to the magnitude of the force vector multiplied by the distance through which the object moves, multiplied by the cosine of the angle between the force vector and the displacement vector. We have learned about the work kinetic energy theorem. The work kinetic energy theorem says that the change in an object's kinetic energy is equal to the total work done on that object by all forces acting on the object. Okay? Finally, we have learned about the idea of a conservative force. A conservative force does a total work of 0 on an object as the object moves around a closed path, and we have learned in particular that gravity is a conservative force. I have here a 1 kilogram object. So how much does a 1 kilogram object weigh? Well, we can use the formula mg. So mass, 1 kilogram, g, 9.8 meters per second squared. mg is then 9.8 newtons. Now, 9.8 newtons, that's pretty close to 10 newtons. Let's just round that off for today and say that this weighs 10 newtons. Anyways, I'm going to take this 1 kilogram object and I'm going to push it through a 1 meter distance as I apply a 10 Newton force, and then I'm going to release the object. Okay? Now, if I take the object and I push it through a 1 meter distance as I apply a 10 Newton force, how much work am I doing? So we're going to apply our formula for work. And so in this case, I have my object. I am applying a 10 Newton force. I'm going to write P because I'm pushing the object. And I am applying that force through a 1 meter displacement. Okay, so how much work did I do? So the work would be equal to, from this formula, magnitude of the force, 10 newtons, times the distance I pushed it through, 1 meters. And in this case, the force and the displacement are pointing in the same direction, so the theta here is 0. I have cosine of 0. Cosine of 0 is 1, so I just have 10 times 1 times 1. So the work I do, pushing the object through a 1 meter displacement as I apply a 10 Newton force, 10 times 1, that would be 10 joules. Now let's actually do the experiment. Okay, got the object here. I'm going to push on the object with a 10 Newton force as I move the object through a 1 meter displacement. Okay, I have done 10 joules of work. So according to the work kinetic energy theorem, when I release the object, it has 10 joules of kinetic energy. Okay? Now, let's say I take the object and I'm going to move the object vertically through 1 meter. Now, wait a minute. When I take the object and I move it vertically through 1 meter, how much work did I do? All right. I applied a 10 Newton force. I'm calling it P for push again. Let's put in the object. I went through a 1 meter displacement. Okay. So the substitution into the formula would be exactly the same as before. 10 newtons, 1 meters, the vectors are still parallel, so we still have cosine of 0. I'm still doing 10 joules of work. Okay, so the work done by the push force in that experiment I just did was 10 joules. So I apply a 10 Newton force through a 1 meter displacement. I did 10 joules of work. but this time, no kinetic energy. Why was it that when I do 10 joules of work on the mass, moving it horizontally, I get 10 joules of kinetic energy, but when I do 10 joules of work on the mass, moving it vertically, no kinetic energy? What happened here? Let's go back to the light board. I guess what I have left out here is the gravitational force. Remember from the beginning, we're going to say today that an object with a mass of 1 kilogram, we're rounding it off and we're saying that it weighs 10 newtons. So let's put in that gravitational force. All right, so how much work was done by the gravitational force? Well, this time the calculation is going to be a little different. So the work done by the gravitational force would be, use the formula from here, magnitude of the force, right, equally strong, still 10 newtons. The displacement, still 1 meters. And going on to the next line here, I have the cosine factor. Now, what is the angle between the gravitational force and the displacement? Well, notice that those are opposite here. So I have cosine of 180. Cosine 180 is minus 1. So how much work was done by the gravitational force? It would be 10 newtons times 1 meter, which is 10 joules, but then times minus 1 gives me minus 10 joules. So that's what happened. As I moved the mass through that 1 meter vertically, even though I was applying a 10 Newton force and doing 10 joules of work, gravity was applying a 10 Newton force in the opposite direction, doing minus 10 joules of work. The total work done was 0. So I'm feeling ripped off now. When I do 10 joules of work in a horizontal push, I get my kinetic energy. When I do 10 joules of work in a vertical push, where's my kinetic energy? Oh, there it is. Somehow I got my kinetic energy back. But how much kinetic energy did I actually get back? Well, let's see. Gravity is a conservative force, so gravity does a total work of 0 on an object as the object moves around a closed path. Okay, so think about that motion of the mass here. I start from the table, I lift it up, I drop it back down, comes back to the table. That's a closed path. I start and end at the same position. So gravity did minus 10 joules of work on the way up. How much work must gravity have done on the way down so that the total work would be 0? Well, on the way down, gravity must have done plus 10 joules of work. Now, how much kinetic energy did the object have when it got back to the table? Well, when I released the object at the top, it had 0 joules of kinetic energy. No other forces were doing work on the object on its way down. Gravity did 10 joules of work, so the object must have returned to the table with 10 joules of kinetic energy. So when I do my 10 joules of work in a horizontal push, I get my 10 joules of kinetic energy out immediately. When I do 10 joules of work in a vertical push, gravity took away that kinetic energy I was expecting to get, but gave it back to me later. So what have we learned here? We've learned here that when I do work in opposition to a conservative force such as gravity, I store that energy, and that energy can be recovered later on as kinetic energy as the object returns to its initial position. Potential energy is energy stored by doing work in opposition to a conservative force. Gravitational potential energy is energy stored by doing work in opposition to the gravitational force. So in the next video, I'm going to introduce you to formulas that we can use to calculate gravitational potential energy, and then we're going to learn how we can use gravitational potential energy to solve problems that so far we might not have been able to solve by any other method.